All right, greetings YouTube, beautiful mind here. We're continuing our discussion on calculus, our introduction to calculus. We're continuing chapter 1 of differentiation. And here we're going to be looking at section 1.3, average rates of change. The objective here, some objectives here are to compute an average rate of change and to find a simplified difference quotient, okay? So let's see what these are. Let me minimize this for them. So let's start with some definition. As x approaches a, let me see. As x approaches a, the limit of f of x is L, written again. We have the limit as x approaches a of f of x is L. If all values of f of x are close to L, for values of x that are sufficiently close to but not equal to a, all right? So the idea here is that, again, with limits, we're concerned with how a function behaves or how the y value behaves as x gets closer and closer to some number. We're not really concerned with, when we're talking about limits, we're not concerned at the point, we're just concerned on either side of that point. On either side of that x value, how does the y behave on either side? Like, is the y approaching the same number as it approaches from the left and from the right, or is it not, right? So that's kind of what we're concerned with here. So then now we have, let's see what we mean by the average rate of change of y with respect to x. As x changes from x1 to x2, is the ratio of the change in the output to the change in the input, right? So in college algebra 1, you know, for our discussions, average rate of change essentially was just the slope, right? So slope is like rise over run, or change in y over change in x. So whenever you see average rate of change, essentially we're just talking about the slope between 2 points, right? Because you can see it here. You know, here's the first point and here's the second point, right? Again, with the 2 points, the two x values are not equal. So average rate of change for this context is just the slope, right? That's essentially that's what it's been. So then if we look at the graph of the function, we see that y2 minus y1 over x2 minus x1, again, y2 is just f of x2, y1 is f of x1 over this, right? Which is both the average rate of change and the slope of the line from P to Q, right? From these two different points. The line through PQ is called the secant line, right? So we have some curve that we're considering, and we have 2 points on this curve, P and Q. So then we essentially just want to consider the slope of the line, of the secant line that passes through P and Q, all right? So we have average rates of change, again, change in y over the change in x, which is the same as f of x2, this is just y2, minus f of x1, that's just y1, over x2 minus x1, right? Okay. So in this example, for y equals x squared, find the average rate of change as x changes from 1 to 3, right? So we have two different x values. We could find two different corresponding y values. We could find, again, average rate of change is essentially just the slope, right? So short. I just don't see it, but it's okay. So let me see. I'll just call it y average. It's something like this. The average rate of change. So again, that's going to be, we can call it y2 minus y1 over x2 minus x1, right? So then y2, let's let x2 be 3. So if we plug 3 in, 3 squared is going to be 9 minus 1 over 3 minus 1. So y2, I probably should label these, but I let x1 be 1 and I let x2 be 3. So then when I plug in 3, I get 9. When I plug in 1, I got 1. So then I just did y2 minus, So then what we get is 8 over 2, which is 4, right? So as x goes from 1 to 3, the slope is 4. Now let's see what happens as x goes from 1 to 2. The change is going to be y2. So 2 squared is 4 minus 1 over 2 minus 1. 3 over 1. Generate some more space for myself. And then for part C, so when we plug in 3 squared is 9, minus 2 squared is 4 over 3 minus 2. We got 4. You know, I didn't check it. I just kind of did it kind of quickly. Here's some type solutions. Let me see the average rate of change. So when x1 is 1, then y1 is 1. When x2 is 3, y2 is 9. So then they get 4. I think we got the same result. Then they get 3 and 5, right? We're essentially just finding the slope between those 2 points, okay? So here we have a quick check, and we're asked to state the average rate of change for each situation in a short sentence. Be sure to include units. It rained 4 inches over a period of 8 hours. So inches per hour, right? So if you did, okay, a short sentence, if it rained, average rate of change, so the slope, if it rained 4 inches over 8 hours, then we can express this in inches per hour. So if we did 4 over 8, so half an inch per hour. So it rained half an inch every hour. All right, I'm just gonna write half an inch as a shorthand. Inches per hour. Miles per gallon, right? How many miles do we get to every gallon? Your car travels 250 miles on 20 gallons. So then we can do 250 over 20. You can, okay. So if we did 250 miles over 20 gallons, we can lose that trailing zero. So then 25 divided by 2 ends up being what, 12.5 miles per gallon. 12.5 miles per gallon. Is it 1 L? Let me look because it's driving me nuts. It's 1 L. So then that means we traveled approximately like 12.5 miles per every gallon. At 2 p.m., the temperature was this. At 5 p.m., the temperature was this. Okay. Let me think about this one. Okay. So we can do this like degrees per hour, right? So then the second one, we could say 76. We could say 76 degrees minus 82 degrees. Seems like the temperature is dropping. And we could say basically 5 p.m. minus 2 p.m. It's a difference of 3 hours, right? So we should get the temperature is dropping as the time is progressing. The temperature is dropping, so we should get a negative result. That difference is what, 6? Because it's like 4 and 2 is 6, so that's going to be a negative 6 degrees for every 3 hours. So then it's going to be negative 2 degrees every hour. Right. So basically, what we're saying is that the temperature is dropping by 2 degrees every hour. Again, just average rate of change of the slope. And let me do the following. I think I need to go back and like edit the beginning part of this video, but it took me so long to figure out how to like stream this without this weird echo in my ear, and it was like driving me nuts. I felt like that scene in Matrix 2, I think it was, where like Neo met the architect. It just kept repeating in my ear. It was so weird. Anyway, okay. And I know I didn't write it in sentence, but again, I think this makes sense, right? So let's just look at it. So the average rate of change is, so the average rate of rainfall was half an inch of rain every hour, right? The average miles traveled in the gallon was 12.5 miles every gallon, okay? And then the average change in temperature was -2 degrees every hour. I think that's exactly what we got. Okay. So for f of x equal x cubed, we're asked to find the average rate of change between, okay, as x goes from 1 to 4, 1 to 2, and then 1 to 1.2. Notice that that second point is getting closer and closer to 1, right? The first point is x equals 1. The second point, first we did 4, then we did 2, then we did 1.2. So that second point is getting closer and closer to the first. So let's see what happens to the average rate of change for this function as the second point gets closer to the first, right? So average rate of change, we got our x1 and y1. I'm actually going to go ahead and label these. I'm going to call this x1, x2, 1, 2. So then let's find the corresponding y1 and y2. So then y1, when x is 1, we get a result of 1. And then y2, when x is what? 4 times 4 is 16 times 4 is 40 plus 24 is 64. Basically 4 to the power of 3. Because it's basically 4 times 4, so 4 times 4 is 16. So then I was doing 16 times 4, which is the same as 10 times 4 plus 6 times 4. So it's 40 plus 24, that's why I got 64. Okay. So all the y1s are just 1. We probably should change the label of these y2s, but I think we can keep it straight. 2 cubed is 8. Now 1.2. 12 times 12 is 144. 44 is 1440 plus 288. 1440, 1728. 1728. 1728. Think about it. Maybe like this. I'm gonna have to use my calculator here. Hey Siri, what's 1.2 times 1.2 times 1.2?
2 times 1.2 is 1.728.
Look at God. Look at God, right? So, this technology is really an extension of our natural abilities. Like because we spend so much time looking outwardly and we never go within, we don't ever like cultivate our abilities, our natural talents and abilities. Um, if you ever just wanted to find something interesting to watch, like on YouTube, which is like that's like the interesting hub, um, do a YouTube search for human calculator. And like there are just like some fancy ways that people like crunch numbers in their head, and it's just fun. It's just fun. Like it has applications and things of that nature, but it's just fun anyway. So you heard how I did that one. 12 times 10 times 12. I know 12 times 12 is 144. So then I was trying to do 144 times 12. So I broke it into 144 times 10, which is 1440, and then 144 times 2, which was 288. Those I can do quick. So then I was trying to add 1440 plus 288 as best I could. And this is what I got. And then I knew it was something with the decimals. I was going to come back and do that at the end, but okay. Anyway, long story short, just having some fun. So now we got an x1 and y1 for each set or each part. So then the average rate of change is just the slope, right? So I'm just going to put that here. Y2 minus, let me call it M average. It's like the average rate of change or whatever. I'm just saying Y2 minus Y1 over X2 minus X1, right? That's what we're going to do. So then for part A, I just should check and make sure that this is streaming properly. I'm not going to, I'll just trust it. I'll have to do it. Well, no, because last time that happened, it was so exhausting. I did the whole thing and then, fix something that's not broken. I have to come back and like Trim the intro. Oh man, that was so weird. I probably should keep that blooper and just save it. Okay, so for part A, average rate of change, right? So y2 is 64 minus 1 over 4 minus 3 over 3, which is 21. All right. So this is base. So this is like I'm geeking over here. I know I'm like calm. One, it's like 3 in the morning here. My lights are, it's 3 in the morning, but this is the first time I've like streamed directly to YouTube from an iPad without the computer because the computer like it has this weird quality. I've been trying to figure out how to improve the quality. I should be able to do it with my equipment without having to purchase like new equipment. I'm kind of geeking. It's actually working. It seems like it is anyway. So that is 8 minus 1 over 2 minus 1. That's going to be 7 over 1. So it's just 7. I'm going to put 2 over here. 1.728 minus 1 over 1.2. That's going to be 0.728 over 0.2. We could multiply by 1 in the form of 10 over 10. This would give us 7.28 over 2. I think this will be okay. And then let me think about it. Okay, how many 2's are in 7 is what, 3, which is 6. So that's going to be how many 2's are in 12 or 6? How do we do? So these are the average rates of change we got. We got 21, we got 7. Notice that that slope is getting smaller and smaller and smaller. It's tending towards like 0 or some other number really. It's just, but it is getting smaller. First the slope was 21, then it was 7, then it was 3.64. Let's see how do we do. See the 21 there for part A, 7, and then 3.64 for part C. Okay. So we've explored limits. Again, limits we're concerned with what happens when as x get closer to some number. We're concerned with how does the y behave as x gets close to something, right? But we're not concerned with that point. Then today we kind of revisited average rates of change, which is essentially just a slope between 2 points. And then in the last example, we kind of explored the average rate of change as a second point gets closer and closer and closer to a first point, right? So now we want to take that notion of finding the slope as a second point gets closer to the first, and we want to extend it a little bit further. We want to push the limit, right, of that concept. So the average rate of change of f with respect to x is also called the difference quotient, right? So again, difference quotient is just the slope between 2 points, right? Where h is not 0. So say we have some f of x, some x, right? Some x value and some corresponding f of x, right? Then we want to introduce some change. We're going to call that the change h. So now we started with x. Now we have x plus h, right? Again, the y corresponding with x is just f of x. The y corresponding with this guy is f of x plus h, right? So then we have this one point x comma f of x and this other point x plus h comma f of x plus h. So now all we want to do is find the slope between those 2 points. Y2 minus y1 over x2 minus x1. Again, y2 minus y1 over x2 minus x1. That's all this is, right? So if you list that out and simplify, you'll get the difference quotient. Again, this is just the slope between 2 points, where h is some small change in x, right? H is just some small change in x. Again, If we do y2 minus y1 over x2 minus x1 and simplify, we'll get the difference quotient. Okay. So the difference quotient is equal to the slope of the secant line from this point to this point, right? Hopefully that was okay. I tried to like, you don't have to get too bogged down into it. I'm just trying to introduce it and give you a good foundation. You're not, the way we're doing it in maybe this section and the next section, that's just for those sections. Once we get past those, we're gonna talk about a lot of shortcuts where the stuff that's gonna take us like a page to do, we're gonna be able to look at the formula and just produce the answer. I just want to try to get you through this. I don't want you to get too bogged down into it. I just want you to kind of like consider it. All right. So in this example, so for f of x equal to x squared, find the difference quotient when x equals 5 and h equals 3, right? For these two scenarios. I think I will need some more space. I'm going to give myself some space. I'm going to add. I'm a fan of. So difference quotient, right? So the general form of the difference quotient, I'm just going to say dq. The difference quotient is f of x plus h minus f of x all over h, right? So then for part A, x is 5 and h is 3. X is 5. I was losing power. I guess I can. I guess if I notice a change. Let's see. And then let me check this really quickly. That looks okay. Oh, now I want to make sure that the audio is working because I had to switch out my headphones like when it was done. Let me just make sure it's still working. Give me just a moment. I'll just make sure the audio is still working. Okay, I think it's working. Okay, ooh, keep it going. And we said H was what? 3 for the first one. Okay. Let me check one more time. 3, okay. All right, so find the difference quotient, right? So let's find each part. Let me see, what's our f of x? F of x equals x squared. Okay. So let's first find f of x plus h, right? So then that's going to be f of 5 plus 3. So that's going to be f of 8. So that's going to be 8 squared, which is what, 64, right? I'm going to highlight it like this. So that's our f of x plus h. Let's go ahead and find f of x. Okay, that's going to be f of 5. So 5 squared is 25. Okay, there's that part. I think we already have h, so let's just plug this stuff in. So then I'll just say the difference quotient is going to be f of x plus h, which is 64 in this case. 64 minus f of x, which is 25, over h, which is 3. If that were 30, that would be what? 34 plus 5 is 39 over 3, which is what? 13. So we got a, so for part A, we got a difference quotient of 13 with those conditions. It just seems like when I go to stream, everything, all the sounds are like exaggerated. I don't notice them any other time. It's just when I go to stream. And then part B, the only difference is now that H is 0.1. So now that change is much smaller. So then B, X is 5, H is 0.1, f of x is x squared. Okay, let's just do the same thing. If we consider f of x plus h, that's going to be f of 5 plus 0.1. That's going to be f of 5.1. I don't know 5.1 times 5.1. I'm just going to use a calculator. Hey Siri, what's 5.1 times 5.1?
5.1 times 5.1 is 26.01.
Okay. And then we want what f of x? We know f of x, okay, just for the sake of space. And then I think we have h as well, so then we can go ahead and evaluate our difference quotient. Okay, that's going to be x plus h, which is this 26.01, minus f of x, which is 25, over in this case is 0.1. What is that, 1.01? Over 0.1. I'm going to multiply top and the bottom by 10. If I do this, this just gives me 10.1. So then this is the difference quotient that we get. So I guess I got to get a better table and chair. My table and my chair both make a lot of noise. I can't move like without them squeaking and squealing. Okay, let's do like this. Let's fix our paper. We're gonna put it back to plain. And I think we're good to go. So for part A, we got 13, and part B, the slope is like about 10.1, okay. So A, they got 13. I think they did the same thing we did. Okay, and then part B, 10.1, same thing we did, okay. So for f of x equals this, find a simplified form of the difference quotient. Okay, so again, for the difference quotient, it's going to abbreviate it like that. F of x plus h minus f of x all over h, right? So now let's plug in the components. Okay, so f of x is x cubed. So now we want to plug x plus h into f of x. We're going to have x plus h cubed minus x cubed all over h, right? We want to simplify this, okay? So if we expand that x plus h cubed, I used to know a shortcut, but that's okay. We're going to do x plus h times, now if we square it, we'll have x squared plus 2xh plus h squared minus x cubed all over h. Okay, let's keep going. Now, if we expand that, it's going to be what? X cubed. Let me think. Okay, so then x times x squared, I'm going to do h times x squared plus x squared h, right? And then plus 2x squared h plus 2xh squared plus xh squared plus x cubed, right? Over h, okay? So then if we combine like terms, we get x cubed plus 3x squared h plus 3xh squared plus h cubed. Oh, and I'm forgetting my minus x cubed here. Let me shrink that down. How is it going to capital H? Under. Let's start about here. Let's do. Okay. All right, cool. I just want this here. Cool. Sorry, I've just been a little bit meticulous. Just because I can. Okay, I feel better about that. So for combine like terms, and actually I am going to go ahead and cancel these guys out. So that gets rid of this guy here. Now what's left over? We got 3x squared h plus 3xh squared plus h cubed, right? So when you're, simplifying these difference quotients, notice how all these terms still have an h in them after you simplify. That's how you know you're on the right track. Like more often than not, as long as you have an h in each term. So now what we're going to do is factor out an h from each term in the top. So we can factor out an h. And we're going to be left with 3x squared plus 3xh plus h squared over h. And again, this is just like, I don't want you to get too bogged down in these difference quotients. It's not always going to be like this. Like all this work that you're seeing to fill up this whole slide, we're going to be able to do it in like the blink of an eye. Like you can bypass all of this stuff and just jump straight to the answer. Okay, we have some proper, this is building up to this idea or concept of differentiation. And at first glance, it is kind of intimidating, especially with difference quotient. But once you get past that and you get into some of the shortcuts, it gets fun. Well, to me, it gets fun, and it's much faster. It's much more smooth, right? So these guys cancel. It's like shortcuts. We have a ton of shortcuts that get you past all this stuff. And this leaves us with 3x squared plus 3xh plus h squared. So remember that h is just some small change in the x, right? So once you get comfortable with this idea of the difference quotient, you're ready to get the concept of differentiation. The derivative is nothing but, well, I'll just say it for now. It's the slope of the tangent line at a point, right? So thus far, we talked about average versus change, and we looked at the slope of a secant line. A secant line is a line that intersects a curve at more than one point, right? So we've been exploring secant lines, and we were also considering as that second point gets closer and closer to the first, right? So then all we do for differentiation is to keep going. So as a second point gets closer and closer to the first, then what's happening is the slope of that secant line is giving us a better and better approximation for the slope of the tangent line at a point. The only difference between the slope of a tangent line and the slope of a secant line, the slope of a secant line is basically the slope of a line that intersects a curve more than once. The slope of a tangent line is the slope of a line that intersects the curve at one point, but it like grazes and bounces, it kind of grazes the curve, right? We'll see it, but that's essentially what the derivative is. The derivative is the slope of the tangent line at a point, right? It's like the instantaneous rate of change or the rate of change at one point, the slope of a tangent line at a point, all right? And then when we start finding formulas or functions, the derivative function, that basically tells us the slope of the tangent line for any given x value, right? So we can generalize it. Give me just a moment. It's probably gonna cut off. I got to give it a few more minutes. That's fine. I got my lights programmed to cut off at like 3:30 in the morning, but I think it's gonna do it again in like 3 minutes. So I'm gonna just wait to turn it back on. Okay, I'm gonna do it anyway. Hey Google, change the light brightness to 40%.
All right, setting two lights brightness to 40%.
Okay, so I think we got the same thing. 3x squared plus 3xh plus h squared. 3x squared plus 3xh plus h squared. Hopefully that wasn't too intimidating. We have a type version of what we just did. You know, we plugged in x plus h, we expanded it all the way out, canceled like terms, combined like terms, and then factored out the h's and they canceled. And this is where we ended, right? Okay. So now use the result of example 3 to calculate the slope of the secant line. Average rate of change at x equals 2 for 0.1, 0.01, and 0.01. Notice this change is getting smaller and smaller and smaller. That second point is getting closer and closer and closer to the first point, right? So now with the previous one, we got, let's copy what we got earlier. 3x squared plus 3xh plus h squared. We got 3x squared plus 3xh plus h squared. Again, this is our difference quotient. So now we actually use the result from example 3 to calculate the slope of the secant line. Okay. So when x is 2, okay. So then we have these 3 different h values. So then first we'll consider when h is 0.1, all right? Let me see one other thing. Yeah, I just didn't feel like writing all that. Okay. I'll say the difference quotient. I'm just going to abbreviate it like this. This is going to be 3 times now x is 2 squared plus 3 times 2, and h is 0.1 in this case, plus 0.1 squared, right? 4 times 3 is 12. There it is. Hey Google, change the light brightness to 40%. I gotta go and change those settings.
Okay, setting two lights brightness to 40%.
2 squared is 4 times 3 is 12. 3 times 2 is 6. What is that? 0.6, yeah. So plus 0.6 plus 0.01, right? So 12.61. Okay. Okay, I'm gonna go with it. Then 0.01, h equals 0.01. The difference quotient is 3 times 2 squared plus 3 times 2 times 0.01 plus 0.01 squared. 4 times 3 is 12. 6 times 0.01 is 0.06. You know it's a 1. I think you have to have 4 decimal places, so 0.123, like that. All right. For the sake of space, I'm just going to put it here. 12.0601, it looks like 12.0601. So notice is for this instance, on x is 2, as h gets closer and closer to 0, you should notice something about this difference quotient is getting closer and closer to some number. Right? Again, the way we're doing it is just to kind of give you some context or background information. I don't really want you to get bogged down in all of this. This is just for like context. In like a week or two, we're not even really going to be doing it this way. And then h equals 0.001, right? So then the difference quotient ends up being 2 squared plus 3 times 2 times 0.001. 001 squared. 12 plus 6, 0.006 plus, it should be what, 6 spaces? 1, 2, 3, 4, 5, 6. Let me just put it here. 12.006. 001, right? It's getting closer and closer to 12. So as that h gets closer and closer, as that change gets closer and closer to 0, this slope gets closer and closer to 12, right? Okay, that was an adventure. Looks like it's still connected. So we got 12.61, 0601. Uh-oh. Oh, there it is. 006, 001, right? So for f of x equal this, find a simplified form of the difference quotient. Okay. So here, let me do it this way this time. Let me see, the difference quotient is what? F of x plus h minus f of x all over h. I'm gonna call that star, right? Instead of abbreviating it as dq or whatever, I'm gonna call it star. Okay. So then we can say that star equals, now if we plug in x plus h, we're gonna have x plus h under 3 minus 3 over x all over h, right? Okay. So we can get a common denominator, or yeah, let's just get a common denominator. So then x times x plus h. We can multiply the top and bottom by x times x plus h to cancel out all the fractions, right? Actually, the least common denominator of all the denominators. Let me think about it. Here, let's do. Let's just combine this into one fraction first. I was just trying to think of which order I wanted to do all this stuff in. Let's get the top, combine it into one fraction. So a common denominator is going to be x times x plus h, right? So then this first one, we have to multiply the top and the bottom by x. The second one, we have to multiply the top and the bottom by x plus h. Because again, we're just multiplying by 1 in this form so that we can get it into the form that we want, right? So then if we do this, the first one becomes 3x minus 3 times x plus h, okay? The bottom is still h, so now let's flip and multiply. And let's combine some more like terms. So we can distribute that -3. So on top, we're gonna have 3x minus 3x minus 3h. On bottom, we're gonna have h. Let's write it as xh times x plus h, okay? So on top, this cancels this, right? Now notice we have an h that we can factor out that can cancel. If we were to factor out an h after that simplification, basically this h is going to cancel this one, okay? So then what we're left with is on bottom we have x times x plus h. On top, I think we still have that -3. Okay, I think that's it. It was a little bit of an adventure, a little bit of a stretch. Again, this is why I was trying to I don't want you to get too bogged down into this, because I know for students it could be intimidating, and you have to basically be neat, space it out, give yourself plenty of space, because if you try to write too small and cram, it's easy to miss stuff. Okay, so we have some prepared notes for this part. Let's compare it to our prepared notes and see how do we do. We got -3 over x times x plus h. Okay. Okay. So you can see they get the 3 over x plus h minus that. I think we got the same thing. All right. Okay, we're gonna let that be. Okay. All right, so hopefully that wasn't too terribly bad. We made it through it. So just as a quick summary, an average rate of change is the slope of a line between 2 points. Again, it's just the slope of the line between 2 points. If the points x1, y1 and x2, y2, then the average rate of change is y2 minus y1. If the 2 points are solutions to a single function, an equivalent form of the slope formula is f of x plus h minus f of x over h, where h is the horizontal difference between the two x values, right? H is just some small change in x. This is called the difference quotient. The line connecting these 2 points is called a secant line. Okay, the difference quotient is the same as the slope formula. Both get the slope of the line between 2 points. The difference quotient gives the average rate of change between 2 points on the graph, represented by the secant line. It's preferable to simplify the difference quotient algebraically before evaluating it for particular values of x and h. Okay. All right. We made it through that adventure. Okay, guys. So hopefully that wasn't too terribly bad. Stay tuned, and we're going to go ahead and start the stream for the next section. Okay. On that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.